In this video, we are going to talk about an application of line integrals to find the center of mass. So many structures in mechanical systems behave as if their masses are concentrated at a single point that is called the center of mass. So when we're doing calculations involving a system of objects, it can be helpful to find the center of mass. And I'm going to abbreviate that COM. So let's first look at the case where we just have two masses. So I'm going to place them on an x-axis. So at this point, I have an object of mass m1. And at this point, I have an object of mass m2. So somewhere on the x-axis, I have my origin. And then I'm going to call this x-coordinate x1. And where the second mass is, I'll call that x-coordinate x2. So conceptually, the center of mass is a point where if I were to think of this as like there's like a rod here on the x-axis that has no mass, and then I place these two masses on it, the center of mass is a spot where if I were to balance that rod that has these two masses on it, it would perfectly be balanced. So if those two dots had the same mass, I would expect the center of mass to be exactly halfway between. But if one of them is way bigger, to balance it, I have to be way closer to the big one. So when do these balance? So I'm going to take this distance, which is, I'm going to call this x coordinate the center of mass, x with a bar on top, minus this x coordinate. So that's one of those distances. I will label this d1. And then the other distance, x2 minus x bar, I will call it d2. It turns out that they are going to balance if m1 times that first distance equals m2 times that second distance. It turns out, we can verify this through experimentation, but that's what makes it balance. If we plug in for d1 and d2 into this and we do some algebra, it turns out that x bar ends up being m1 x1 plus m2 x2. So the masses are getting weighted by these positions divided by that total mass. So this is what's called a weighted average. Center of mass is the weighted average of the mass's respective locations. Okay, so let's go one step up now. What if we have n of these masses and they're distributed along a single axis like this with x coordinates x1 up until xn? So let's draw a picture. So let us draw a single axis like this. And along that axis, I'm going to place several masses now. Maybe the first one, I'll call this mass m1 at the x coordinate x1. And then a little bit after that, maybe a much bigger mass, which I will call m2 at the x coordinate x2. And then much further down the road, maybe I have a much smaller one that I'll call m3 at the x coordinate x3. And then I'll draw two more. So two more, maybe this one I'll mass is m4, and this one maybe is a little bigger. This one's m5 at the x coordinates x4 and x5. So the center of mass, again, is going to be some point where, if I place these masses on a rod like this, it would be that balance point where it perfectly balances. And I will call that x coordinate x bar. There's a very similar equation we could set up for where these would balance. It turns out that the end result for x bar is going to be very similar to this. On the top, I'm going to be summing up each mass multiplied by its x coordinate, and then all of those added up. So I'm going to need a sigma notation to write this. So I'm going to be summing up mi times its x coordinate xi, and the sum goes from I equals 1 to n, from mass number 1 to mass n. And on the bottom, it's just the sum from 1 to n of the masses, just sum the masses on the bottom. Okay, so now let's go one step up, which is, what if now the wire itself has mass? It has some variable density function, rho of x. So let's draw a picture. let us draw a picture. So imagine I have an axis here, and I'm interested in measuring the mass starting at some point when x is a up until another point when x is b. I'm interested in finding just the mass of this portion from a up until b. I'm going to shade in the part that I'm trying to find the mass of. So, we have a way to handle this if there were like n discrete point masses. But here I have like infinitely many points along the way. So the way we're going to do this is to chop this up into pieces. So chop up the wire into n pieces. Let's chop it up into pieces. Chopping it into pieces. Don't worry about drawing the exact same number of tick marks as me. Just make sure you have several. And I'm going to call the length of each one of these pieces delta x. So all these pieces have length delta x. And then I can approximate the mass of each of the pieces. So let me focus on this piece for the purposes of a drawing. I'm going to call that piece number I. And its mass I will call mi, and I'm going to try to approximate it. To approximate it, I will take some test value on this interval. So maybe I'll take this point and I'll call that x coordinate xi. And even though the density is changing throughout here, as long as these pieces are reasonably small, it's a fair assumption to assume that, the density is kind of close to constant that whole way, even though that's not quite the case. That's what's going to give me an approximation. So let's plug in this x coordinate into our density function. So I will get rho of xi for my density, multiply that by the length, delta x. And density times that length, that gives me my mass, my approximation for the mass. So let us use this with our formula from case 2. So I'll get my x coordinate of the center of mass. This is going to be an approximation. I'm going to get a fraction. And up top, I'm going to get the sum from I equals 1 to n. And then I have to write my mass, which I have approximated here. It's rho of xi, my density, times that delta x, that length, times xi, the x coordinate of the point. And on the bottom, I am summing up from 1 to n of mi, which, again, I have the approximation of. It's rho of xi times delta x. Okay, so we have this set up here. Right now it's an approximation. To make it exact, we take a limit. So now we take a limit. We are going to let this delta x, that length, approach 0. And when we do that, our x coordinate, now it's perfectly going to be equal to, and it turns these Riemann sums into integrals. So my integral goes from a to b, right? Those are the start and end points of my interval. And then you change these xi's to x's. So let me write the xi at the front, x, and then I'll get rho of x, and the delta x becomes a dx. And on the bottom, I'll get the integral from a to b, and then change the xi to an x, and the delta x becomes a dx. And there we have it. That's our formula for the center of mass here. When my wire is a straight wire and it's got some density function. Okay, so now let's take this one step up, which is in our multivariable land. What if this is a curved wire in space with some density function, rho of x comma y comma z? So let's draw a picture. So I'm going to let's draw our 3 axes here. So z-axis straight up, x-axis slanted like this, that indicates it's coming out of the page, and then y-axis straight to the right. And now I'm going to draw some curve. So there's some curve that exists in 3-dimensional space. Maybe it loops around, and then maybe it loops around again, and then it continues onwards like this. So some curve C. Now, when we talk about the center of mass, the center of mass doesn't just lie along one axis. The center of mass is going to be at some point in three-dimensional space. So it'll have an x coordinate, a y coordinate, and a z coordinate. But I can start it off in the same way. Let us chop up the wire into n pieces. I'm just going to focus on one of the chopped pieces for the purposes of the picture. So maybe it's chopped. Let me focus on this piece. And I'm going to say this curved length is delta s. So each of these pieces will have a length of delta s. And let's approximate the mass of each piece. So this piece, I'm going to call it piece number I. Its mass, mi, I can approximate by, if I look at that piece, I'm going to pick some point on the piece, and I'll label its coordinates as xi, comma yi, comma zi. And just like before, even though the density is changing, as long as these pieces are reasonably small, it's a fair assumption, it's a reasonable assumption to say, let's assume that the density is constant the whole way. So I'll take this point and plug it into my density function. So that'll give me rho of xi, comma yi, comma zi for my density. Multiply that by the length of the piece, delta s, to get an approximation for the mass. So then, to get my x coordinate of the center of mass, so there's one typo here right now. This is going to be an approximately equal to. It's not equals exactly yet. And then similarly, this will be approximately equals, and this will be approximately equals. For all these coordinates, the formulas are very similar. So I will just write it down for the first and just tell you what it is for the others. So it's going to follow this type of format that I had here, where let me write the x coordinate first. So I'll have the x coordinate xi. That'll get multiplied by this density. So the density rho of my point, xi, comma yi, comma zi, and then times the length of the piece, which now we are saying is delta s. Cool. And on the bottom, it'll just be the density part and that length of the piece. So on the bottom, it's sigma of rho of xi, comma yi, comma zi, times the length of the piece, delta s. Okay, and then for the y coordinate and the z coordinate, what's changing is the xi changes to a yi and then zi respectively. So if I want to make this exact, now we take a limit as that length, delta s, approaches 0. And that'll change these sigmas into integrals. So for that x coordinate, I'll get, this will be a line integral over my curve C. The x sub I changes to an x. And then I'll get my density. So the xi changes to an x, yi changes to y, zi changes to z. The delta s becomes a ds. Same sort of thing on the bottom. I'll get a line integral over my curve, and I'll get my density, so x, and then change those things to x, and then y, and then z. So my density function's rho, not x. And then the delta s becomes a ds. Awesome, cool. And then similarly for the y coordinate and the z coordinate, what changes is instead of x multiplying my density, it'll be y multiplying it, and then z multiplying it. Okay, nice. So we have these formulas. We have these formulas for the coordinates of the center of mass when our wire it's a curved wire in three-dimensional space. Okay. One of the things that I want to point out about this is, before we dive into an example, depending on what the wire looks like, imagine my wire's like this, it very well could happen that when I find the center of mass may not actually be on the wire. It could be off it, which is a little weird. Like that doesn't happen in the case where it's just a straight line. It was on the wire. But when it's curved, the center of mass actually could exist off of the wire, which is a little weird. Okay, so let's look at an example. a wire lies along the curve that's traced out by this position function over the interval from 0 to 4 pi. We've actually seen this position function a bunch in this section. I want to set up, but don't evaluate integrals to find the center of mass of the wire given its density function, this rho of x comma y comma z, which we've also seen before in this section. So to help us not repeat a lot of the same calculations we've done before for this, we've actually worked out the mass of this wire before. Remember, the formula for mass is it's just the line integral of the density function, which ended up being this. So in fact, one thing to point out is, notice in these formulas for center of mass, the denominator is just the mass of the object. And the numerator, it's not quite that, because the densities are also getting multiplied by something. It also turns out the length of the velocity here is root 2. That's something we've also calculated. Okay, so let's start with our x coordinate, x bar. So this is this formula, my line integral over my curve, x times the density function, x rho of x comma y comma z ds, and then all over that integral for mass, which is integral over the curve of rho of x comma y comma z. Okay, so the denominator just represents the mass. And the mass, we've worked that out in a previous problem. It's this whole thing. So let's write that out. The mass is just 4 root 2, that quantity multiplied by 5 plus 2 pi. Okay, and then up top, let's convert this line integral into an integral. Like, how do we evaluate a line integral? Well, t is going from 0 to 4 pi, so 0 to 4 pi. And then the way I start my line integral is we plug in our parameterization into this function. So first, for the x here, I plug in the x coordinate, which is cosine t. So cosine t. And now I got to plug that parameterization into my density function, which is here. So for this x, I got to plug in the cosine t, my x coordinate of the parameterization. For the y, I got to plug in sine of t. And then for the z, we got to plug in this t. Okay, so let's do that. So I'm multiplying several terms, so I'll put a parentheses. 5 minus x is cosine t, minus y is sine t, and then plus z is just t. Close the parentheses. Need a little more room, and then remember ds? ds is the magnitude of velocity dt. We figured out the magnitude of velocity in a previous example. It's the square root of 2, and then I have dt. And this problem, thankfully, just said set up the integral. We don't have to evaluate it, so we can stop here. If it actually wanted us to evaluate it, we'd have to keep going with this. But thankfully for this one, it doesn't want us to keep going. It just wants us to do the setup. The other coordinates are so similar that I think it would be repetitive to write both of them down. All that changes is on the numerator, instead of x multiplying my density function, it's either y or z. So then I plug in either the y coordinate or the z coordinate from my parameterization in for that portion. I've also just gone ahead and written out, well, how do you do the length of the velocity? You take the derivative of the position function, and then you find the length. So we had done that in a previous example, but I've written it out fully here as well. So this big old square root thing, that is what is simplifying to square root of 2. Okay, so we've done this example. I want to end with a special case of this, which is, what if our density is constant? So I'm going to call that density just equal to a constant k. We call the center of mass then the centroid. So here's my formula for the x coordinate of the center of mass. In fact, there's one typo. I've written the equal sign twice. So let me cross one of these out. And let's simplify this. So I get a line integral over my curve, x times my density function, which we are saying is just k, and then I got the ds. And then on the bottom, I just got the line integral over my curve of the density function, which is just k, ds. The k's are constant, so I can pull them out in front. So I can pull the k in front of the top integral, integral of x ds. I can also pull it in front of the bottom integral, times the integral over c of just ds. I guess technically there's a 1 here. And then the k on top and bottom cancel, which is really nice. So I get the line integral over my curve, x ds, over, on the bottom, just the line integral over the curve of ds, or I could call that 1 ds. Remember that this integral in the bottom, line integral of 1, that's the arc length. And what we have here is a formula we've kind of seen before. This is actually the formula for the average value. It's the average value of whatever function is here on the top, which, so x, so the average value of the x coordinate, average value of the x coordinate along our curve. So if I had some curve with a constant density, it would be telling me like, well, what's the average of the x coordinates along the way? Okay, so similarly, for my y coordinate and z coordinate, the center of mass, it's got the exact same structure, except just change that x up top, either to a y or to a z. So, okay, so this is the centroid. What the center of mass becomes simplifies to if the density is just constant. So I really want to emphasize that I can only cancel these densities here because it was constant. Because it was constant, I was able to pull them out. If this part's not constant, I cannot pull it out and I wouldn't be able to cancel them. All right, so in terms of our goals for this section, we've made it to the end. We did things out of order a little bit, but we finished the last goal. How do we calculate the center of mass of a wire?